All right. Hi, everybody. This is a video for internal forces and moments. And in this problem, we're given this funky beam. It's got a roller support and a pinned connection and an applied moment, and then some applied forces in weird directions. So this is a little bit of a challenging problem in the way that it's set up. And we're asked to do a few different things. So what we want to solve is for the internal forces and moments at plane CC, and that's just to the left of the force transferred between the beam and the support, and then plane DD, which is just to the right of that force. So we call this kind of like exploring both sides of the knife edge. Knife edge support is a word that we would use for this type of situation. So we want to solve for at C. We want to solve for N, V, and M, normal force, shear force, and bending moment, and at D, D, solve for the same thing. And since we're solving for multiple planes, we want to show subscripts. So kind of the long way to do it would be this way. Those lowercase letters are showing that we have a cut plane, um, but that gets a little bit tedious. So I'm going to use these types of notation. Just use a single subscript for simplicity as I work through the problem. Okay, and so the idea is that at plane CC, lowercase, there is node C. So I'm just going to kind of put node C right here, node D right there. And then that lies at the centroid at cut planes CC and DD. Okay, with that in mind, let's do plane CC first, and that one's going to prove to be the easy one. Here's the free body that's looking really appealing to me. What I want to do is come right here, grab all this stuff, and just deal with this. And the reason why this free body is appealing to me is because I don't have to solve any reactions at A or B in order to compute what these internal unknowns are. I don't need to solve for any internal reactions. Move this up just a little bit so it looks a little more conventional. Right, there we go. Okay. So all I need to do here is introduce my internals. So internal normal force, positive tension, arrow away from the body, positive shear force up, down. This plane is down. So that's my positive internal shear force and my positive internal bending moment on this plane is counterclockwise. Now remember, for all these internal force problems, we have the two different sign conventions. So we've got equations of equilibrium, so the ones we've been using. So we'll be like, this way is positive, this way is positive, and this way is positive. And then we have our internals, okay? So this is defined as positive, that's defined as positive, this is defined as positive, and to be able to go back and forth as the problem continues. I'll leave that up there for now, I think. Okay, so we are ready to rock and roll with this. We've got a free body, it's in static equilibrium, so we can run through our equilibrium equations. The first one I'm going to pull out is going to be summation of forces, and the x direction equals 0, rightward is positive. And here I'm going to have 1, 2, 3 terms in that horizontal force equilibrium equation. So positive 9 minus 6 plus n is equal to 0. On the left side, 9 minus 6 is 3. Move it to the other side, I get n equals negative 3 kips. We could also express that as 3 kips of compression. expression. Those are the two ways to express that idea. Um, we probably could have done that one by inspection as well, but no harm in writing out the equations and kind of developing that problem-solving procedure. So let's do a summation of forces in the y direction equals 0, upward is positive. I've only got two terms here. So by inspection, I'm anticipating v is equal -4. Let's go ahead and write it out and make sure that we understand the process. So minus 4 kips, that's downward, minus v, that's downward, set it equal to 0. V is equal to -4 kips. And the best way to express internal shear force is with the negative sign. Do not use a single arrow. If you'd like to use a double arrow, you could do it like that, right? That's a negative shear force. The plane on the left tends to move down. The plane on the right tends to move up. That's a negative internal shear force. So one of those two would be okay, but really the preferred way to do it is just with the negative sign. Lastly, summation of moments about the cut plane is equal to 0. And so that node C that we invented right there, we're summing moments about the z-axis that's coincident with C. And we're going to use our equations of equilibrium sign convention, counterclockwise positive. And how many forces are going to cause a moment about C? We're going to have 1, 2, 3, and 4. So we'll have 4 terms in our moment equation. First term, 4 kips, moment arm, 3 feet, sign, thumbs up, positive. Next term, 6 kips, moment arm, 1 foot, sign, thumbs up, positive. Next term, 9 kips, moment arm, 1 foot, sign, thumbs up, positive. Last term, my moment at C, my moment at C, what I want to solve for, and that one is thumbs up, positive. Set that equal to 0. Okay, so I'll run through the calculator operation for this one. So I have 4 times 3 is 12. I'm going to add that with 6 and with 9, and then move it to the right side of the equal sign to get -27 for my internal moment. The 3 sig figs, that would be 27.0. Kips times feet are my units. All right, so those are the plane CC is pretty straightforward. Really, the only curveball is how to deal with those horizontal forces. But that, all the basic principles of static equilibrium still apply. We are looking good so far. I'm going to go ahead and turn that one off. And I'm going to turn this one off. And maybe I'll hang on to that one, but I'm not sure I need it right at this moment. All right, so there's our loading diagram again. And now we're ready to tackle the internals at D. And regardless, like when I come out here with my cut plane and I cut through plane D, I have to pick either the left side or the right side. And either way, I'm gonna get a reaction in there. So I have to do equations of equilibrium on the whole thing in order to make this work. So let's go ahead and do that. This free body is like this. So we'll take the entire member, including this little doohickey here. Okay, so there is the body I want to isolate. And applied loads, so I've got the 4 kips, the 6 kips, the 9 kips, the 5 kips times feet, and now I need to put in the reactions. So you can do some qualitative equilibrium if you'd like to do that. Let's see. There's A, there's B. So B sub x through qualitative equilibrium is pretty easy. We just need to oppose these forces. I've got net force pointing rightward. So I'm going to assume that I've got my B sub x reaction pointing leftward over there. And in terms of the verticals, I've got ups or downs, and we're going to make those assumptions on the free body diagram. And I'm just going to go on autopilot here, and let's just assume that they're both upward and use the math to verify whether or not those assumptions are correct. I've got A sub y and B sub y. All right, B sub x we can do by inspection. So I'm going to make that equal to 3 kips leftward to balance out the 3 net kips of load that's happening over here. And then for the verticals, I've got to do a moment summation. And I can pick either A or B, and I'll pick A for no real reason. So the summation of moments about A is equal to 0. And we're going to use our equation of equilibrium sign convention. Counterclockwise is positive. And we can do our accounting. How many terms are going to be in this moment summation? 1, 2, 3, 4, 5. We're going to be solving for B sub y. And even though B sub y is pointed upward in my free body, I'm just going to reiterate that as part of my problem solving process, that I'm going to put By in the equation, assuming that it's an upward force. And if I get a positive sign, then that assumption will be verified. Okay, let's do it. So my first term is going to be 4 kips. That's at a distance of 3 feet. And that one is positive. My next term is 6 kips at a distance of 1 foot. That one is positive. My next term is 9 feet at a distance of 1 foot. That one is positive. My next term is the 5 kip feet. Okay, so these are all in kips times feet. And so we're going to add in 5 kips times feet. And that one is clockwise negative, thumbs down. And lastly, B sub y, its moment arm of 8 plus, just 8, moment arm of 8. This is in kips times feet. And the sign for that one is going to be positive, thumbs up, counterclockwise, set it equal to 0. And just let my calculator run through this. All right, so I've got a 12 plus a 6 plus a 9 minus a 5 equals times -1, move it to the other side, divide by 8. And I get -2.75. The negative sign reverses my assumption that By is upward. So -2.75. Okay. And oh, let me fix one thing with the units actually. So this is in feet here. That's why my answers is back to kips, right? Because I divided everything by the feet. When I did that, divided by 8 feet, so I get back to kips there. All right, here's the best way to communicate this ambiguous nature of signs in statics and mechanics problems. So since I assumed it was upward, when I report this answer, I want to reiterate that that was my assumption. So I want to come back and say, okay, it's -2.75 kips upward. And then to be crystal clear about the answer, I'm just going to immediately turn that back around and say, which is the same thing as 2.75 kips downward. That's the best way to communicate that effectively. All right, and the rest of it is easy, so we can do a quick force summation in the y direction equals 0. And I've got -4 plus ay, and I'm just going to write here again my assumption. So assume ay is upward. So -4 plus ay. And then when I get to by, like the true nature is downward. So minus 2.75. These are all in kips. Set that equal to 0. All right, so I've got my -4 minus 2.75 times -1, move it to the other side. And so I get 6.75 at A to balance all of this out. Okay, and we got a positive sign, so that validates that this is an upward force. And so it's pretty easy to communicate that when you assume things correctly. Okay, so we are looking good here. And now that we're ready to dig in plane DD, I can use either free body. And the one that's most appealing to me is the one on the right. So if I cut it DD, I'm going to make a new layer. So if I cut it DD, and I'm going to run that free body all the way until I get to B. I need my reactions at B. So I've got 3 kips leftward and 2.75 kips downward. My load is an applied moment on that segment. And now we get to the cut plane. So as I cut through, I introduce the unknown internal forces. Those take the place of the actions of everything that I've cut away. We always draw these in the positive direction for internal forces. This is what we sketched out a little earlier, not that one, this one. Okay, so we're using those sign conventions for internals. So we're using this side of the plane, tension arrow away from the body, shear upwards, moment clockwise. In the same way that for our other free body, we use those for our positive direction of the internals. So take extra care to draw those correctly and always in the positive direction on your free body. All right, now that we have a free body, we are ready to go again. So I'm going to zoom out a little bit, give myself a little bit more room, and we can solve this one pretty quickly. So the summation of forces in the x direction equals 0. Can you do this one by inspection? So N equals 3 kips compression by inspection. If you wanted to write out the equation, you'd say minus N minus 3 equals 0. Therefore, N equals 3 kips. Okay, summation of forces in the y direction equals 0. Oh, and I'm forgetting my subscripts again. I'm so sorry. So this is N sub D, N sub D, N sub D, V sub D. And that means D is the node. Node is just like a way to label point. So D is the centroidal axis of plane DD. Plane DD is just like think of it as like a rectangular surface. All right, back to business. Summation of force in the y direction equals 0. Upward is positive. First term V sub D, upward positive. Next term 2.75 kips, downward negative. Set that equal to 0. Therefore, V sub D is equal to positive 2.75 kips of shear force. Lastly, summation of moments about the cut plane is equal to 0, counterclockwise positive. And how many terms? 1, 2, and 3. The other ones are coincident. So we just have 3 terms in my moment summation. Just working from left to right, first term m sub d. That one is clockwise negative, thumbs down. Next I have my 5 hips times feet. That one is clockwise negative, thumbs down. And then I have 2.75 kips at a distance of 8 feet away. And that one is negative thumbs down clockwise. Set all that equal to 0. Okay. Negative 2.75 times 8 minus 5. I multiply by negative 1 to get it on the right side of the equal sign. And then I divide by negative 1 to isolate m sub d, and I get a moment of negative 27. You may remember that that's the same answer we got for CC. So as we cross and go from CC to DD, what we see is that the internal normal force stays the same. The internal bending moment stays the same, but the internal shear force is different because of that vertical reaction A sub Y. I think that's all I need to say about this one. Thanks for tuning in. Have a great day.